Assalamualaikum, Profesor.
Waalaikumsalam warahmatullahi wabarakatuh.
Professor Iqbal, we can start.
Okay. Okay, we can start.
We start now, inshallah.
We are waiting the coordinator general to start. Okay, few moments.
I came available, you can start anytime.
Okay. Excellency, honorable speakers, esteemed colleague, dear expert and dear participant, Assalamu alaikum and good morning.
Waalaikumsalam warahmatullahi wabarakatuh.
I am Dr. Hakim Sokou, Senior Program Manager, OIC Comstech. It is a great honor to me to moderate this webinar. First of all, I would like to express my highest consideration to you all for your presence here today with us. Nothing is lost, nothing is created, everything is transformed. It is with this basic statement of French chemist Antoine Laurent de Lavoisier, I would like to welcome you all. This hybrid webinar entitled Innovative Technologies for Recycling of Liquid and Solid Waste, an alternative for protecting the environment and driving economic growth, is organized under Comstech Forum on Environment and Ecosystem Restoration. Before going into the scientific intricate of this subject, which is certainly interest of us, kindly allow me to invite my dear brother and colleague, Mustafa Zain, Senior Program Manager, to bless us with a few verses of Holy Quran. Dear Mustafa, please join me. Thank you.
أعوذ بالله من الشيطان الرجيم أمن هو قانتنا آناء الليل ساجدا وقائما يحذر الآخرة ويرجو رحمة ربه قل هل يستوي الذين يعلمون والذين لا يعلمون إنما يتذكر أولو الألباب صدق الله العظيم.
Jazakallah khair. Thank you, my dear brother Mustafa Zain. Now, I would like to request His Excellency, Professor Dr. Mohamed Iqbal Chaudhry, Mustafa Laureate Prize, Coordinator General of OIC Comtech, for his welcome remark. Please, Professor, the floor is yours.
Auzubillahi minash shaitanir rajeem. Bismillahir rahmanir rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning and good afternoon. First of all, let me express my gratitude to three very competent, qualified and world-renowned experts who are joining this panel of experts in this important hybrid webinar. Professor Dr. Godfrey Zamaju, dear friend of ours from Benin. He is the director of Regional Shanghai Center, as well as an iconic person for his achievements in the field of sustainable agriculture. He has been a symbol of innovation and resilience. Despite all the constraint, Dr. Godfrey has achieved what no one was able to achieve in the field of sustainability in the field of agriculture. Professor Dr. Muhammad Arshad, Associate Dean of the Institute of Environmental Sciences and Engineering from the National University of Science and Technology, is also a leading expert from an institution who is one of the best institutions in the Islamic world. And certainly very important, dear Professor Dr. Bao Indrawan, brother. He is the director of Center of West Management Indonesia, from a very friendly country, and someone Professor Hakim has actually mentioned very high about it. Hakim, I'd like to appreciate your efforts also, and I would like to welcome all the participants online in person for joining this important innovative technologies for recycling of liquid and solid waste and alternative for protecting the environment or driving economic growth. The topic is extremely important, very close to my heart, because this is something which goes into one of the most enduring challenges of today's world. Waste is the most important problem when it comes to resource depletion, as well as environmental issues, and that has to be solved with the introduction of technology. I'd like to take you a bit more on how this whole problem started. And that again is a gift of colonialism, and firstly a curse which we all still suffers with. Colonialism started from a wasteful industrialization because they had unhindered, unabated access to huge resources of 95% of the world, which was under colonial control between 15th to 19th centuries. And this uncontrolled, unabated, and unlimited access to raw material and resources has generated industrial paradigm which was linear and wasteful. So what has happened was that industries were developed which produced less from more, and that has created the whole concept of waste. Similarly, we see that this was a complete paradigm change, because in our cultures, in the world of Organization of Islamic Cooperation and developing world as a whole, we had a culture which was sustainable. We didn't really believe on wasting things. It was a message of our religion. It was a message of our tradition. And so the entire thing was changed, and they introduced their own products, including plastic was introduced by them, which is the curse of colonial era today, from pottery to different things. And this has created an environment in which we have piling waste, which we don't really know what to do with. And if you look into resource depletion and consumption, this goes on even today also. 80% of the world resources are consumed by 20% of the world population. And as a result of it, you see a complete disrespect of what is happening to the resources of the developing world, which hardly can benefit from that. sustainability is in great threat because we are leaving nothing for next generation. And this is where Dr. Akim has actually arranged this very important seminar for which I really appreciate his contribution. He would like us to discuss how can we convert waste, which is certainly not waste, it is a cyclical process where waste of a process, one process is a raw material for the other one. And this closing the loop is extremely important. And that is where technology plays an extremely important role. We see it in Shanghai and many other places where they have closed the loop, where nothing is wasted, or at least very little is wasted. And technological development plays an extremely important role. And through this webinar, we would like to start this discussion, a dialogue of how can we use technologies for converting so-called waste into useful product. It is not only needed to solve environmental problem, it is equally needed to control resource depletion, because resources are depleting extremely fast. And if we don't really use what is available, then we are in a great loss. We would need many planets in order to sustain the consumption pattern which we have developed for ourselves also. For comstech, it's extremely important that we have created a forum for the environment and ecosystem restoration. And through this forum, such important topics need to be discussed. This dialogue need to be initiated. And who can be better moderator of this discussion than the three panelists of today? With this, I'd like to thank you all. I hope that you are aware of contributions of comstech. Please do visit comstech website, see what program we are launching, and my very competent colleague sitting in the hall also would be very happy to provide you information about many, many programs which comstech has initiated. I expect that this webinar would eventually lead to a much larger dialogue platform, and we can have a global conference on at the OIC level to discuss what we can do, what are the technologies available which are adaptable and affordable. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Professor, for your insightful and inspiring speech. You have highlighted the challenge of the moment related to waste production and while emphasizing way to benefit from it. In this spirit, we have with us today the qualified experts to share their knowledge, their expertise with us for sustainable development. Ladies and gentlemen, with your permission, we will now head to Indonesia, where our first speaker of the day is located. Professor Dr. Bayu Indrawan, who is the founder and director of the Center of Waste Management Indonesia, lecturer at the University of Indonesia, University of Jambi and Nusa Putra University. Besides his scientist expert, Dr. Bayu Indrawan is also the philanthropist who established the Al Jazari Foundation, a non-profit organization committed to social and humanitarian causes through education, health, economic support, and character development. Dear Professor Indrawan, the floor is yours, please.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My voice clearly here?
Yes, yes.
Okay. Good afternoon, ladies and gentlemen. It's a honor to join you today at this important comstech forum on environment and ecosystem restorations for this amazing days. Greetings to Professor Muhammad Iqbal Khodari, Coordinator General of OIC Comstech. Thank you, Dr. Akim, for the invitations. Greeting also to other distinguished Professor Godfrey, Professor Arshad as the next speakers, and all respective participants. So grateful for the chance to share Indonesia progress toward a circular economy, as Professor Iqbal before mentioned about the circular economy, the terminology. So where the technology and innovations are transforming into our waste management ecosystem. So today's my presentations will be an innovative waste to energy by hydrothermal and pyrolysis technology, advancing circular economy on OIC member states, and it will be focuses on practical solutions so that turn waste challenges into opportunities for a greener and more sustainable future. Next. So before I start my presentation, allow me to introduce myself a bit. Dr. Hakim before already introduced me. I am Bayu Indrawan with 20 years of experience on energy and environmental sectors. I hold a doctoral degree in environmental science and technology from Tokyo Institute of Technology in Japan, specializing in waste to energy and renewable energy. As a founder and director of Center of Waste Management Indonesia, and also I'm a regional chair of WTERT. It's a global council that focus on advancing sustainable and technology-driven waste management. So I also have led some commercial implementations of what will be discussed today about hydrothermal and pyrolysis technology for waste to energy. It's including the first integrated municipal waste facility in Indonesia that we built in 2014. As I also mentioned, I also a lecturer from Universitas Indonesia and another university. It's driving me an innovation at intersection of science, technology, and education. Okay, we align our understanding first about waste as worthless. Waste now is now viewed as the resources. Recently, it's become a resources as a source of energy, source of materials, and innovations. That there are three key terms that we already usually hear every day about recycling, turning waste into a products, and then many things that we still have a huge landfill in every country, especially in Indonesia. Also, we still do open dumping, sanitary landfill. Also in mostly of Islamic country like Pakistan and other things, we still relies on the disposal sites, many of open dumping sites. Then that's become a opportunity as a resources that we need to treat. So another terminology about a zero waste as a mindset to cut waste through the recycling, resources, and composting, for example. So with this shared view, we can build a smarter and more sustainable solution for our communities. As a waste management use different method, as we know that depending on the waste type, the characteristic itself, desired outcomes, and the product itself. So the common approach, it will be include landfilling, incineration as a waste to energy composition, compaction, reduce volume, but it's less effective from organics, biogas, and everything. That each methodology has its strengths and its limitations. For example, the waste energy is high capex, capital expenditure. So we need to make it more suitable for us to use the each composition or each technology that we more right mix in key of the effectiveness and sustainable waste management. So today we'll be more focusing on waste to energy implementation. The waste to energy transformation from waste as a resources into energy through various processes. As we know, recently there are 4 commercial implemented waste to energy technologies, mostly in incineration, direct burns waste to produce the electricity or heat. That another things, gasifications, as applies heat with a limited oxygen to generate syngas for energy. And also that we have been developed between these decades is about hydrothermal and pyrolysis. It's utilized high temperature with pressure without any direct combustions, and also the pyrolysis use heat waste without oxygen to produce three product, gas, oil, and also another solid residues. So today our focus will be two key technologies of waste to energy landscape, especially in hydrothermal and pyrolysis. So these are not only areas that we have been developed significantly expertise, but I personally consider the pyrolysis and the hydrothermal among of them the most promising and practical solution for our country especially, and also for sure for another Islamic country for the current existing waste challenges, because most of us mostly mixed waste. So let's start with pyrolysis. Maybe some of you already know about the pyrolysis. Pyrolysis is thermal decomposition of organic materials through heating and the absence of the oxygen. So the pyrolysis have three outputs, mostly syngas, biochar, and bio-oil. So this technology have advantage. For example, it's capable converting the various waste types and including plastics, non-organic, and everything that burnable. But mostly the pyrolysis should be a homogeneous type of waste that can be effectively treated for using pyrolysis. Another advantage is produce energy and also a high valuable product, like I said before, biochar, syngas, or bio-oil. And also it support the circular economy because it's generate the product. So on 2013, we have been successfully implement the first commercial scale of pyrolysis technology in Indonesia. It marking a significant milestone to utilize the waste for energy at the commercial scale. So here the engineering design, for example, for a pyrolysis reactor that we have been developed with a capacity approximately 1 meter cubic reactor for semi-commercial implementations. And also we have been developed many plan before. So let we a bit more technical about the policies itself. It begin with loading the waste into the reactor where it's heated and with a high temperature, but there's no direct combustion like incinerator. Incinerator is direct combustion, but pyrolysis is like on the without any oxygen, so it's not direct burning. Roughly 300 to 900 degrees Celsius with oxygen. So this transforms waste into energy, oil, gas, and also the solid residue itself, the charge itself. So mostly that many implementation recently for the plastic to oil implementation about the pyrolysis. So the generated gas condensed into oil, and then while its condensable gas is used as energy for sequence processes, the char itself can be utilized as fuel, and also mostly if it's raw material is organics, it will be can be become a fertilizer. So this is a sample of the operation schematic of the pyrolysis technology that we have been developed before. Due to the time constraints, I think I will skip this section for now. But if some of you, however, if some of you are interested in discuss more technical, we can explore more further during the Q&A session. Okay, and maybe okay, this one of the sample, the example of the pyrolysis product from in the form of bio oil. It's produced by heating the plastic or organic waste. It also can be like a PCB from electronic waste, or rubber for the from the wheel. So this process results a high energy oil content, comparable to the kerosene, gasoline, or diesel, like industrial diesel oil that we have been usually use as usual. So this bio oil can be used as a alternative fuel for machinery or energy generations. It's offering more environmentally friendly as a substitute of fossil fuel. So here, let me pass it this. This is the sum of our portfolio before about the pyrolysis technology, which have been implemented in several countries. Since 2009, I've been supporting the Japanese company called Shinko Holdings. It's the first company as a reference about the technological transfer from Japan. For Japan, it's implement the first commercial pyrolysis technology company in Japan. And then we implement some of in the several countries like Japan, also China, Saudi Arabia. Also, we have some pilot commercial plan, Vietnam, Sri Lanka, and many others country. So that's about the pyrolysis. Next, we move to the more interesting technologies called hydrothermal. Usually people say HTC, hydrothermal treatment carbonizations. So we have been implemented it commercially in Indonesia since 2014. The hydrothermal process itself treating mixed waste. So like pyrolysis is suitable for homogeneous waste, but this hydrothermal is suitable for mixed waste. It's including mixing with organic, also plastic, and another waste. So I will show you some videos later on for make better picture and better imagination of how this technology works in commercial plant. So this is using the water in the form of saturated steam. In a high temperature, roughly 150 to 250 degrees Celsius with high pressure. Like before, a pyrolysis without pressure, but more higher temperature. But in this case, a hydrothermal, more lower temperature, but with high pressure, roughly 15 to 25 bars to 30 bars of pressure. So the advantages of this hydrothermal treatment, including its ability to process a wet organic waste without any need for drying, because as we know, mostly our waste on the developing country like Indonesia, Pakistan, and others is mostly mixing waste with the capacity of the characteristic of waste itself is mostly organics. 70% of organics with moisture content roughly more than 70 to 80%. So it's producing environmentally friendly products and reducing a greenhouse gas emission compared to landfills and another conventional technology. So this technology can process various types of waste, such as municipal solid waste, agriculture waste, organic waste, and another type of waste. So one technology, one black box can be treated with several types of unutilized resources: agriculture, municipal, organic, sewage sludge, and other things. And also the product itself can be many things. Can be like coal like solid fuel, like biochar itself. There's solid and liquid fertilizer if the raw material itself is mostly organics, and then also a livestock or animal feed. So with this technology, we can create the zero waste ecosystem, that all of this waste So for example, municipal solid waste can be used as a fuel, as energy itself. For agriculture also, we can have some crop from vegetable and fruits. But using this technology, we can use fertilizer. We can produce the fertilizer for livestock industry, and this kind of technology can produce several products, and also the raw material itself can use the several option of raw material. So this is the most promising and the most efficiency technology that that can be implemented for the mixing waste itself. So next, this is the drying process. Only with around 30 minutes, 40 minutes process, the mixing waste can become like a slurry product, and easily to dry. Roughly 1 day to 2 days natural drying, it will become like 10 to 20% moisture content. The characteristic itself is similarly with coal. So we can also another things use it as a liquid fertilizer, and also solid fertilizer for the end product itself. Using one technology, using one equipment, we can produce many things of product. So this is the example of the application is for co-firing with coal. The product can be replaced the coal, or blending it for co-firing in power plant, in cement kiln, in paper mill, steel plant, or other implementation that usually they use another biomass or another coal. It's replaced with this biomass from municipal solid waste. So this is more technically, we can mix roughly 20% of this product, replacing the coal itself, and there's no significant change of the characteristic combustion. It can be implemented in cement kiln, mixing with the coal, using mixing bunker, and pulverize it, and use it as a biofuel. This is some layout that it's not required a huge land. For example, in our first commercial plant, it's the capacity itself around 100 tons per day. It's only required 2,000 meters square area, including the drying process, including the mobility process. So only 2,000 meters square. It's very small plant that can be treat good amount of municipal solid waste. I will show you the video later on. So this is our first commercial plant that I said before. On 2014 we developed it. Okay. This is the product analysis. If we compare the municipal solid waste and the product itself, it's roughly 17.9 megajoule per kilogram, or roughly 4,500 kilocalorie per kilogram. It's good enough for replacing the coal. But if the plastic is higher, we can get a more higher calorific value of the product itself, because as we know, the plastic contain the high calorific value. So here, for example, the mass balance, I will skip this one. The energy balance also very good, only use roughly 10% or 11% of the product itself, sorry, 13% of fuel. Product itself can be reused as a fuel. So it's like a very sustainable system, because we don't need too much energy from outside to do this system. So mostly the energy balance of as we know, most energy balance of this system is from the heating of the steam itself. The heating of the steam itself will be become from the product itself. Roughly maximum 15% we return back to the system, and another 85% of product we can sell it to generate the income. So another's like electricity, and then another utility is not so much using in this technology. So because this developed by before in Japan, for sure, Japan is very strict about the environmental, because this also developed in Department of Environmental Science and Technology. For sure, the most important thing is about the environmental concern, about wastewater already passed the standard itself, and also the gas emission also already passed the standard. Yeah, for sure, the environmental concern will be the priority for sure. And I think before to make clear about this technology, to provide more concrete understanding of the hydrothermal technology, I will share the factory video that illustrates its process and product outcomes. Okay, you can see the video, yeah. Okay, in 2014, this is the first implemented hydrothermal technology in Indonesia, which has since become the national and also global reference as a country first integrated waste processing facility. Many colleges from US, from Australia, from Europe also visit our commercial first plant about the first recycle system of hydrothermal. So the process begins with the input of fuel-derived fuel, like you see before. It's categorized as biomass, much of like agriculture or plantation waste. So next, the biomass is processed in a boiler system to generate high-pressure steam. So initially, the waste is fed into the reactor via the loading and area and hopper. It contains various types of waste. You can see many plastic there, many durians there, many food there. It's mixing waste, and then it can be processed on the reactor, inside the reactor, only like 10 minutes to 20 minutes with the high pressure, around 20 bar, and then it's discharged. Output from the reactor, it consists of uniform, like you said, uniform black powder that dries easily within maximum 2-3 days with natural drying. The moisture content can drop below 10%, and the next product can dry in greenhouse more faster, can be forced hot air, but more efficient using greenhouse, and the product can be briquetting, pelletized, or keep it bulky, depending on the needs of the consumer demands. So this process, organic product can be also turned into a solid composting, which can be implemented for landscaping, reducing the need of expensive external fertilizer, and also the product itself can be sold as a replacement of the coal. So I think that's all my short presentations about the hydrothermal and pyrolysis technology. I think it's already 20 minutes. Yeah, finally we jump to the conclusions that the hydrothermal and pyrolysis technology itself offers an innovative solutions for waste management by efficient reducing the waste volume and also the converting into a valuable product. So these technologies also generate renewable energy, helping to reduce our resilience on fossil fuel. Moreover, the play of key roles is to promote the environmental sustainability by minimizing pollutions and greenhouse gas emissions. So it can be support our effort to create a cleaner and more sustainable future. So that's conclude my presentations, we will now move to the Q&A sessions. Please feel free to ask any questions related to the topic discussed, and I will be happy to provide further insight. Thank you very much.
Thank you, Professor, for your insightful lecture, and it is great honor to us to have you today. Now we will give the floor to audience to ask their question. Okay, please come.
Professor. Thank you so much for your lecture. As you mentioned about the different methods for the waste management, I'm interested in knowing about the hydrothermal method of the waste management. If this method make the fertilizer from the waste that include the plastics and the other type of organic waste, so that type of fertilizer may be, I guess, harmful for the soil fertility. And before this method, if it is not as that type, as this type, do the factories and the you can say the workers do the filtration process before going toward the hydrothermal power? Yeah, if you mention about this process.
Okay, got it. Okay, I answer directly or waiting another questions? I answer, yeah. Okay, like if it's for fertilizer, mostly the raw material itself, hopefully it's all of it is organics, because we cannot put some a bit plastic is okay, but not so much too much plastic. It will be not good for the plantation itself. Like before, we use for less than 5% of plastic is still okay for fertilizer, but more than 5% is not so good for the fertilizer itself. And also the heavy metal content on the battery and other thing, it will be dissolved on the water. So the product of solid itself, it's easily to replace it, to separate it between solid and liquid, because as you see, it's become like a sludge. It's sludge itself, the liquid itself will contain the heavy metal content, the chlorine content if it's in plastics or another. For example, for agriculture, roughly the problem is the potassium content. The potassium content will be dissolved on the water, and the solid itself is clean from the like chlorine or potassium, because as a solid fuel, we cannot accept a high ppm or high content of chlorine and potassium. But for agriculture, for fertilizer, we need the high potassium content. So the liquid itself can be used as a fertilizer, and the solid itself can be used for the biomass or replacing coal. I think it's answered your question.
Yeah, thank you so much. I have another question.
Okay.
Will you please briefly explain, or you can say a two-line explanation of what do you think about the wastewater management, like municipal waste to the sewage waste?
Yeah,
Which
sure.
method is useful? Yeah.
Sure, the wastewater is as some part of the system itself. We have very simple wetland that more effective and more efficient, not high cost. Using the wetland itself, we treat the wastewater, and the contaminant is under the standard of wastewater itself. But if it's organics, it's no need to go to the wastewater, because the liquid itself is a fertilizer, liquid fertilizer. But if it's heavy metal contents, it will become to the wastewater treatment. For
Okay.
sure, on our system, we have the wastewater treatment after the steam discharge and after the liquid separate. If it's high heavy metal content, it will be to the wastewater. But if we only treat the organics, for example, landscape, only landscape, it's no need. No need to go to the wastewater. The liquid separate as a liquid fertilizer.
Okay, so do you think that landfill method is more dangerous for the underground natural water resources?
For sure, the landfill itself is just a time bombing. We cannot rely on because we have a limited area, for sure, especially on the big city. It's only time bombing. If we not recircular it, if we not doing a circular way, using a technology, for sure, it will become a time bombing.
Okay, thank you. Thank you so much for your time. Thank you.
Thank you for your question.
Right. Thank you, Professor. There is some question in the chat box.
Okay.
The first question is Kashif Mahmoud. What is the main uses of product which make it in result of hydrothermal technologies? We can use this soil for plants to improve their growth.
Yes, sure. Like the hydrothermal process, there are three product. Solid solid coal like solid fuel, or we call it biomass, biochar. It's for more bigger capacity because as a replacement of coal. Second, as a fertilizer, but the raw material itself cannot be too much plastic or another contaminant. If it's mostly organic, for example, agriculture waste or landscape waste, yes, we can use as a fertilizer, as a composting, because if we use conventional composting, it's required like 20 days to 30 days of decomposition. Using this hydrothermal, only 20 minutes, you can directly get the product. It's already decomposed. So it shorten the process as a natural process. So another things is like for solid fuel, it's like if we know the coal itself, it's a burden on the soil and push with a high pressure of the push of the earth. 1,000 years it become the coal. This hydrothermal is shorten shorten the duration of creation of the coal. Usually 1,000 years we can make it high pressure using saturated steam, like I told before, 20 to 30 bars. It's like if you have presto cooking in your house, it's like only 2 bars. But using this hydrothermal, it's 20 to 30 bars, 10 times more than that. It will be certainly become like a coal only for 20 minutes to 30 minutes. Hopefully it can answer that questions. Yeah. Another
Okay,
things about.
Okay,
Next.
thank you, Professor. Now we will move to our second speaker.
Okay.
Okay. Our second speaker is Professor Godfrey Zamujo, who is the director of Regional Songhai Center based in Porto Novo, Benin. He was the professor in engineering at Loyola Marymount University and also has been a researcher at University of California, Los Angeles. Dear Professor Muzanjo, Professor Godfrey, please, the floor is yours for your lecture. Thank you. Professor Godfrey?
Yes, remove
Yeah.
that slide so that we can
Remove
share.
the slide. Remove the slide. We can share. Remove that one. We can share from here. Yes.
Okay.
Good. Very good. Yes. Yes. Okay. Okay. Stop now. Hello. Put it for potential.
Okay, you can start, Professor.
Okay. Do you see the screen? Are you seeing the screen?
Yes, Professor.
Okay. 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 Very good. Okay, thank you very much. I would really like to thank you guys for taking, and a special thank you to Professor Iqbal. So this, we're going to take it from my predecessor, a different one, in this case today. So the topic of it, how we're going to reintegrate life from waste to wealth and making matter and energy less finite and more elastic. This is going to be the thrust of what we're doing today. Now, look at it now. Let's present the whole thing, the problem itself. Our present crisis is not merely climatic or environmental, it is civilizational. We have designed a modern world around a false dichotomy. We have urban, peri-urban, and rural as separate competing zones. But life itself does not function in the fragments. The biosphere, real life, operates as a continuum of cycles, energy, matter, and value constantly circulating between systems. This is how it should be done. So we have normalized what is not normal in our present system. When we sever those links, we break the metabolism of life. Our modern cities and industrial centers have become biomass sinks, black holes of consumption. They draw in crops from the rural areas, fish, meat, wood, and water from rural lands, consume them, and then discard them as remnants, waste, solid, gaseous, and liquid. These waste streams, instead of returning life to the soil, become pollution hotspots, breeding disease, poverty, and despair. This is the structural sin at the heart of our developmental model. Now we have to move more from there. This is the curve what is done. You have the rural areas, all of them creating waste, drowning in their waste, all separate. But you see the rural area is being sucked out, all the waste coming from over there. And the urban areas are not recycling, they're sweeping in our waste. So this is what Songa is doing today. Look at, you see, this is what is going on the part of these waste streams, instead of returning life to the soil, become pollution, hotspots, breeding. This is what we cannot take anymore. Now, this is it. Meanwhile, the rural areas, the lungs and womb of our civilizations, are being drained of their vitality. Their soils, water, minerals, and microorganisms are exhausted to feed cities, artificial fertilizer, pesticides, and fossil-based inputs offer only a temporary illusion of productivity, but at a very tragic cost.
Professor,
This
your slide is not moving.
it's not moving. Oh,
Yes, project it and
it's not moving.
yes.
Oh, la, la. Is it moving?
Okay, yes.
Hello? Is it moving?
Yes.
Okay. No, just one before. Yes.
one before. Yes. Do you see this one now?
Yes.
Okay, good. So this is why we have to see at the back one. This is the mess. That's what we are dealing with. It's civilizational. Now this is what we are going over there. Now this is where we are now. Yes. Now this is where we are. Meanwhile, this is what is going on. Meanwhile, rural areas. This is what is going on. Is very, very bad. This, we now, after emptying the rural areas, what do? We now bring artificial input, fertilizers. What do? Those inputs will kill the soil microbiological life. This is the key thing. They weaken the natural resilience and they accelerate pests and diseases. This is what we are fishing today. So we are mining life to feed death. We're exporting wealth, importing poverty. The countryside becomes sterile. The youth flee and the cities swell with hopelessness. This is what we are doing today. Now, the next thing now to do, I hope you're seeing the next slide.
Yes.
Very good. But now, let's now change what we are doing today in this webinar. Turning the waste into life. From waste to wealth, the new metabolism. But look at my brothers and sisters. But if we could reverse the flow, what will happen? What if the urban and industrial waste stream plants, animals, human could become sources of energy and regeneration? This is the key question. My predecessor talked to you about the thermomechanical solution. I'm offering the more biological solution to this one here. I'm glad we are complementing. He offered you thermomechanical. I'm offering a biological system. Through biological biotechnology, using bacteria, fungi, photosynthetic organisms, we transform organic waste into biofertilizers, bioenergy, and biochemicals. This is what is happening over there. Part of these resources feed urban short food chains, urban gardens, and peri-urban farms, while the surplus powers rural and restoration, closing the metabolic loop between the cities and the lake. This is really what is happening to. This is not fiction. This is biointelligence in action in living circular economy. Now, this is now the new sustainable architecture. You see, instead of separating the rural areas, urban and peri-urban areas, we now link them together on the back one. So the recycling on the bottom line, where everything now is in the rural area, there's internal recycling. In the urban area, there's internal recycling, even the city areas, but the bigger recycling, the bigger linkages is over there. This is the new thing. Total recycling, from waste to wealth through this one. But the most important thing is the biological world, where the microorganisms become the key actors to resolve every type of thing over there. So this is what is going on. So now you see, Songhai is a good example. If you look at this now, the second pillar of regeneration lies in redesigning, we call it coupling the energy waste source to other things. You see the crop, that picture, look at it very well. Everything is integrated. No waste at all. Total recycling. This is the future. The microbes at the center, everything is being recycled. Just take a minute to look at them. No waste. This is the new metabolism, where there's no waste. From waste to wealth. Nothing is lost. Everything is transformed. Requires little or no chemical fertilizer, reduces greenhouse emission, increased biodiversity. Is Africa's ecological intelligence rediscovered and modernized. This is what Songhai is doing today, my brothers. We're going to show you a picture of what is happening in the next. So this is what is going on. We are now breeding green rural communities from primary production, where we grow all of them. We call it from the soil to the table. From agriculture, we go to agro industries. Most of the waste in agriculture are recycled and all of them. So this If you look at this picture, my brothers and sisters, this is the future design. This is where we are going. From then, the secondary production, which is agro-industry, all these things are recycled, all of them together, and the tertiary, hotels, but within an ecosystem together, these three units form living ecosystems of employment, prosperity, and dignity. So the challenges today of environmental degradation, unemployment, food insecurity, and job creation and poverty is all solved. The all systemic problem using this new system. This is how we address in one integrated move the environmental degradation, food insecurity and poverty, unemployment of youth and women. This is really what we are doing now. Now, to show you now, the call for action, and this comstech is doing that. The climate crisis is a symptom, not the disease. The disease is disconnection between cities and soil, between technology and life, between economy and ecology. This is the disconnection. This is the real problem. Songai's mission is to heal those fractures by building a regenerative civilization, one where cities feed the countryside with knowledge and energy, and the countryside feed the cities with life and meaning. This Africa can lead this transformation not by imitating others, but by reawakening her ancestral genius of integration, community, and secularity. What began as a small initiative in Port Novo is now a living demonstration that regeneration is not a dream. It is a system that works. Now, so brothers and sisters, let us stop managing decay. Let us start cultivating life so that our cities, our villages, and our planet breathes again in harmony. Now, to show you now, we're going to give you a picture now of how it is happening. Just sit down and enjoy this video. Let's go now. Enjoy it. Okay. Right. This is what is going on. It's working. It's not a show. This is how Songhai looks today. You see the integration. This all young people now, green economy from all over the world coming here. A new system of production, produce more and better with less. You see the circularity. Everything is recycled. From crop to aquaculture to bioenergy, everything. The waste from the thing gives all the energy, and the energy drives all the things. This is the new world. Now let's at the primary production, how is happening. The crop production. Look at the quality. No chemical, no pesticides. Look at it all year round. You are seeing that one. Look at the yam. All the things, the microorganisms. Look at the yam. We are producing all year round. Look at the size of them, almost 4 times the normal size. Through this new ways. Through irrigation, all this recycled water. Look at the productivity. From a dead land, look at the young people now with pride. So we are producing more and better with less. With the cassava, we call them tapioca. We're now having about 70 tons per hectare. No chemical, no pesticides, through regeneration. The waste from this chicken is used for energy and feed again. The litter is also used to fertilize. So this biodiversity, the waste from these animals are now used again. Their urine, everything, even the urine. So this is that Noah's Ark. So look at all the waste from the cows is used now to fertilize the crops. Look at the fish, the wastewater now recycled, all integrated. Look at it within the Songhai. It's from the slurry to fertilize the fish, the water, and grows the algae, and the algae feed the fish. So we are producing more and better with less. So this is a new system. We are making energy elastic by harnessing the solar energy, the biogas, and the wind energy. So all the energy together, you see the young people now, they are making energy elastic. Look at now the gas is being used. We have 1,400 cubic meters of gas, the largest in Africa. 1,400 cubic meters without do them. So that's integrated energy system. What is happening? And then we are producing these machines using our own energy, both boys and girls. Using that energy to transform. Using the waste of that transformation back into the biogas. You see, this is the whole totally. All the recycled metals, using our own energy. We now go to agro industry. The plastic are recycled. Now we're exporting them now. So these are secondary production. Juice and the same thing. So this is a new world. All organic, no chemicals. Now again, from there now to services, hotels, restaurants, and this is what is going on. Now from there now, the produce, we're now marketing them. So we're going to tertiary production. Ice cream, curd, all of them. The waste of this product I used to make something like soap, nothing, carrot soap. Now look at the sausages, look at them. From that one. So we're now going to tertiary ecotourism. We've got all of them together. So that's a new world we are building where everything changes. So agriculture becomes multifunctional, building a new habitat where people can live well within the same farm. So you can, no mosquitoes, nothing at all. So this polyvalent agriculture, then the most important, training a critical mass of young people again to be actors, to be the agency. Look at the wheat. We are producing wheat 3 times a year. 3 times throughout the whole year we are producing. These are the young ones. Look at how Songhai looks. So now have a virtual visit of Songhai size. This is the new economy. The new economy. This is what is going on. It's a total new world. We go to the north. It was dry before. Look at it. We are producing all year round. Thanks to this new technology. So this is another site. All the water harvesting. Look at it now. There was no water there before. We used rainwater to harvest it, to irrigate. So this is what is going on. Water harvesting. Go to another site where many places now are linked together, where everything is integrated. But what is most important is the biological thing. We're unleashing the biological capital, particularly the microbes that do all the work. We call it biomimicry. Let's imitate nature. When we dance with nature, nature will smile at us. So it's a question of changing the way we think, changing the new technology aligned with the way we think. This is another one. We produce rice all year round, 6 tons per hectare, 3 times a year, using the waste from these animals to fertilize them. No smell. And the microorganism transforming them. Look at what is going on in Nigeria now. It's a total, look at the productivity of people. These are the graduates. The green rural communities, we call them. Look at the pride of the young people, transforming all the waste are recycled into new products. Look at the waste from those chicken on the ground. We use them again back into the field to produce. And the most important, the soil is regenerative every day. We're increasing the carbon content. All those grasses, all those shrubs become inputs. The carbon increase. Now look at the color of our corn. We produce corn all year round. Look at the productivity. No chemicals, no pesticides. Now look at the straw again, the microorganisms, and they are transforming everything, recycling everything. Look at the productivity of the corn. So this is what is possible in our world. Without process, we're now processing them now, even the oil from the fish. Now look at what is coming. The wastewater from the chicken is used to feed our fish. So these are the tons going to the hotels. Nothing is wasted. I'm telling you, the wastewater from that chicken processing goes to feed our fish. And this is what is going. Then we market it ourselves. So we're on the driver's seat, our own energy. So this is what SunGuide look like. Look at that carbon you see there. Look at the straw. All of them are fertilizers. Everything is recycled. So we call it 4 for 1,000. We get 0.4% of carbon back into the soil with the microbes. The whole thing blows up. So all the waste are not waste. God does not create waste. The same thing in the fish culture. So this is really what SunGuide is doing. Then I'm going to show you now, not the waste. Look at aquaculture. Look at them. The waste from fish culture were not wasted to share recycling. This is a biological thing. Teaching African communities how to grow fish before teaching them how to fish. This is within our system. We are harvesting the algae.
Professor?
Yes?
Okay.
Okay, you want to stop? You want to stop?
Yes.
Okay, let's stop now. Okay, no problem. Okay, thank you very much. Let's stop here. Thank you.
Okay, thank you, Professor. There is
Yes.
one question in chat box
Yeah.
for you.
Yes.
This
Yes.
question is from Dr. Yolu Muniru. He said, I took part in an activity section in 2019 in Benin Biodiversity Forum. During the section, a small enterprise presented its circular economy innovation, and the company transformed pineapple into juice. The waste generated from the juice product process was used to produce biogas, which served to fertilizing the bottom. The main challenge for this small enterprise was how to store the biogas. I would like to know if there is a way to bottle biogas.
Okay, very good question. The biogas CH4 is a very light gas. So it's not like propane and butane when you can compress it. No. What we think is that you use it on the ground, use it to generate electricity, because if you want to compress it, you'll be using more energy to compress it to go. It's a different logic than the propane or the other type of gas, because it's a very light gas. It needs a lot of energy to compress it. So my advice is to use it on the ground, to use it to drive the city, the farm is really on the ground. Use it to your city where you are to develop the local communities instead of the old model of exporting energy miles away. It's produced locally. We call it the energy really on the ground. So those energy, biogas is to be used locally. That's the most efficient. If you try to compress it, it's going to waste a lot of energy, a lot of gas. It's not very profitable.
Okay, thank you, Professor. There is another other question. Okay, thank you, Professor.
Yes.
For your wonderful presentation. Now we will move to our third speakers, with Professor Dr. Mohamed Ashad. He is Associate Dean in the Institute of Environment Science and Engineering at National University of Science and Technology, Pakistan. He is an agricultural and environmental expert with an experience of over than 13 years as an academician and a researcher. He has worked on different national and international projects funded by local and foreign funding agencies. He has been part of different technical committees at national level and at international level. Dear Professor, please join us on stage for our lecture. Thank you. Where is it? So,
Bismillahirrahmanirrahim. First of all, I would like to thank the comstech team, and particularly Dr. Akim and the chair, Dr. Mohammed Iqbal Chaudhry, for inviting me. In fact, and there have been great talks by Professor Dr. Bayo and Rawan and Dr. Godfrey. So they were wonderful presentations and great work, in fact. And I will be sharing a little bit about what is going on currently in Pakistan, and specifically if we talk about the recent smoke in Lahore, and you might be already seeing the impacts of that smoke, especially in terms of health. So I will be talking about institute stable management through biodecomposite technology, potential for crop production enhancement and smoke reduction. So I will be going quick because we are running short of time. I thought that I will speak a little bit about NUST as well, but I will skip that. I will focus on the topic and then share some of the components of that. With the VN, NUST VN, that is mainly the sustainability and collaboration. We focus on that, and that is definitely leading to so many things. And these are some of the figures about NUST for those people who may not be familiar with the NUST, and we are having more than 21,000 students and more than 1,200 facilities. So that is a rich source where people are working in different domains. And as far as the rankings are concerned, as mentioned earlier, it is one of the top universities in Pakistan. So coming to the introduction of the topic, in fact, the first thing is stubble management. All those people who know about the agriculture in Pakistan, there is a major concern about the stubble, and that is in fact a kind of agriculture residue that is being produced, and that is one of the scenario we see. In fact, if we visit Lahore area, and you can see this something nowadays, because it is happening right now. There is a lot of fire, particularly in the burning of paddy stubble, and in summer season, most of the time we see the wheat burning, straw burning. So what happens if there is such scenario where you see the burning of this stubble? Ultimately, that leads to the air quality deterioration, aerosol production, and this burning, in fact, is a huge component that is not being managed. But there could be certain options, and but people are not going further because there are certain reasons. And what could be the possible consequences of this burning? You can list so many things, but as mentioned in earlier presentations as well, we need to recycle the things. We need to regenerate regenerative agriculture. That is something very important. But these are some of the consequences. For example, if you burn this residue, it can lead to loss of biodiversity, loss of soil nutrients, deterioration of soil fertility, health hazards to human, birds, animals, and greenhouse gas emissions, ultimately contributing to the global warming. So this is the data for this morning. In fact, I took this picture from iqair.com, and you can see the air quality that is not, I would say, a livable quality. And unfortunately, all the 5 top-ranked cities are in the region. So from India, Pakistan, and Bangladesh. So all this indicate there is a huge requirement, or I would say that there is need for a paradigm shift so that we can address this air quality index or ultimately the air quality scenarios and finally health of the people we can improve. This is the picture that was published yesterday by 24 News on their website. That was taken from Lakshmi Chowk in Lahore. So you can see the scenario right now, that is the smoke scenario. In fact, that is due to the mismanagement of this solid waste, in fact. So why we do this? In fact, most of the, you can have so many reasons, but some of the reasons, for example, resource constraint, that could be labor scarcity, financial constraints, time constraints. Because if you go something that is kind of biological systems, they may take some time, and farmers, they don't have time to shift to the new crop, and in fact, they need to burn it so that they can move to the next crop. Farm mechanization, that is also one of the things, particularly in developing world, it is lack of expertise to use state-of-the-art technologies used as combined harvesters, something like that, so that they can recover that stubble of agriculture residue. And specifically, if we talk about Pakistan, that is agriculture is one of the biggest sector, in fact, and contributing around 1/5 of the overall GDP. And so many jobs are related to this. And each winter, about out of 8.5 million tons of rice residue produced at least 3.6 to 5 million tons is burned to clear the fields for sowing wheat. So you can imagine the quantity of waste being burned. And according to FAO, 20% of air pollutant emissions in Pakistan, they are contributed to crop burning, in fact. So these are some of the studies recently done in different cities. If you closely look on the data, the major component or pollution source, that is the biomass burning. So biomass burning is primarily contributing in almost all major cities. So these are different references. If you would like to see into the details, you can go. So what to do, in fact? Ultimately, it is there. Then there is need for on-site treatment systems or on-site management of this stubble. And one of the effort we did, in fact, we tried to have a microbial consortia composed of, that is, we termed as biodecomposer, that is a mixture of fungus and one of the fungal strain, and then with bacterial strains, and all this mixture of or consortium of the microbes is capable of degrading the cellulose, and cellulose is basically the material, cellulosic material that we need to decompose, in fact. And if we are able to decompose it on site, that would be great, in fact. So I will not go into the details into the methodology. These are some classic things we do in the lab. In fact, we prepare inoculum, we prepare the materials required for experimental purposes, and the final objective was to have a maximum enzyme activity, and that enzyme activity, in fact, leads to decomposition or degradation of organic material or stubble. Okay. So for that purpose, we had different types of residues, agricultural residues like rice husk, wheat straw, and then after a certain period of exposure, we were able to do some analysis just to verify what is going on or what is happening, in fact, or what are the outcomes of that treatment, in fact, through different techniques. First thing, that is the most important thing, if we have this cellulose activity, if that is cellulase is being produced by all these strains or these microbial organisms, they can be useful in degradation. Higher the cellulose activity, higher will be the decomposition. So we focus on that, and that's why we termed it filter paper activity, FPA's activity, just a method for measurement of the cellulose activity. So here are some of the results of our study. You can see that effect of different cellulosic substrates on FPA's production by trichoderma, that is a fungal species. So you see after 3 days, there is a decline in FPA's activity. That means production of cellulose is reduced. Initially, up to 3 days, it was going well, but later on it decreased. Similarly, here you see with the Pseudomonas aeruginosa, that is a bacterial species, and that is capable of producing maximum FPase activity at day 4. And that means after that it is decreasing, and that can be attributed to the decrease in the available biomass and also some microbial factors, growth factors in fact. Then here you see the role of Bacillus humulus, that is another species. That is, again, it was similar to the Pseudomonas aeruginosa. That is, we were able to find maximum activity at day 4. For the mixture of the three, in fact, the bacterial strains and the fungal strains, the maximum FPase activity was at day 4. That means within 4 days, that was able to produce maximum cellulose, and we can expect that if that is the scenario, or if we keep feeding these microorganisms, they can produce cellulase, and more the cellulase, more will be the decomposition. So here you can see some of the trends over different days, but overall it was the consortia mixture of the three that was able to produce the highest FPase activity, and the trichoderma, in fact, after 4 days, or for all the three, if you compare, in fact, individual performance was not that good, but as compared to the consortium. So the question remains that what is the percentage decomposition or percentage degradation? So here you can see overall results. After 1 week, here you can see consortia was able to degrade 37%, in week 2, 53%, and week 2 in 53%, and so there was not a big difference between week 2 and week 3. So after week 3 or 2, you can say around 50-55% decomposition was there. And similarly, in case of wheat straw, the results of 2nd week and 3rd week. So you can say the optimal time for this decomposition or for this stubble management would be 2 weeks. So within 2 weeks, we can reduce up to 50% biomass that is available in the field. And so here you can see some of the trends. They are just a little bit replicating, but again, the important thing is that consortia is performing the best, providing the best outcome or best results. So as compared to the individual ones, at certain stages, they were competing with the consortia, but overall performance of the consortia was good one. Just to verify whether there was a decomposition or there was some, for example, here you see the control line for FTIR, the Fourier transform infrared spectroscopy. So you can see that after the treatment with the bacillus, there was a short peak. That means there is a possibility of having new functional groups, and there is a decomposition as compared to the parent material. So similarly, you can see deepening of different peaks, and then also formulation of some new peaks as well. It is on the slide, it is not showing well. Yeah, it has changed some formatting as well. I'm not sure what happened. So similarly, in case of rice husk, here was the rice husk, and similar trends in wheat straw. They confirmed that there was decomposition, there was degradation, and there was formulation of new functional groups with the help of these microorganisms, and ultimately they led to production of some unique metabolic products. When we went for XRD, again, there was a kind of silica formation, or new, you can say, silica formation and organic degradation that happened during this process. And there was some structural changes and crystallization in different when treated with different microbial species. So these are the trends for wheat straw. Similarly, if we closely look into whether there is a decomposition, there is a breakdown. So you can see here on the left side, the rice husk, where there are no lesions, no breakage. But if you look on the right side, where consortia treated, And here you can see there is a breakdown of the structures, and that depicts the microbial action, in fact. Similarly, here you see the scanning electron microscopy for wheat straw. On the left, you have the control, and on the right, you have treated consortia. And if you closely compare the two, you will feel some lesions, some breakdown of the organic material. On the right side, that indicates the microbial consortia was working, and that was capable of decomposing the organic material. So just to conclude that there are some conclusions that can be drawn from this work, that consortia or biodecomposer demonstrated superior enzyme activity compared to the individual microorganisms. Significant differences were observed between the cellulase production capabilities of the different microbes and their consortia for both substrates. Biological decomposition led to the weight loss, where consortia depicted the highest weight loss for rice husk. And then significant structural and chemical changes were observed in rice husk and wheat straw post-microbial treatment. So all these things confirm that there was effective decomposition or degradation. So for the future, we are working on upscaling of biodecomposer and stability testing for better enzyme activity, because if we are able to have these microbial organisms, their stability in the environment, and even if we prepare certain inoculum, we must have a stable inoculum that can be, in fact, used in the field. Similarly, to investigate the molecular mechanism behind the superior performance of microbial consortia, then expand studies to include other agricultural residues and industrial byproducts to assess the general applicability of the product. But before concluding, I just wanted to highlight that at NUST, we have been working on other projects like sustainable development initiatives, including we are moving to the solar energy. Around 50% of the usage is coming from the solar, around 3 megawatts. And then we are targeting net zero carbon. We are working on decarbonization at NUST, and target is net zero by 2030. Then we are recycling our wastewater, and there are different technologies. There is membrane bioreactor technology, and also there is a wetland method. Both are being used for treatment of the wastewater, and around 75% of the wastewater of NUST is being treated and reused, in fact, for different purposes. Then we are using EVs for internal mobility of the students so that we reduce the CO2 into the environment. Then there is a carbon sequestration. Carbon sequestration towers are installed at NUST just to capture the atmospheric nitrogen so that we reduce it. And then we are also working on zero waste, and some of the projects have led to the optimization of different systems for different cities. For example, for Walkend and Murray, we are working to have a circular economy system for the solid waste management in those cities. In fact, these are some of the acknowledgements, and my university, HEC, NARC, our collaborators, and then especially my team, my MS students and PhD students who are, in fact, the workforce for all this work. Then my research group, that is Environmental Biotechnology Research Group at NASP. These are some of the references I used for this presentation. And thank you very much. If there are any questions, please do ask.
Thank you, Professor, for your very wonderful presentation. Now we will give a floor to audience if there is any question.
In fact, I'm standing in between tea and the audience.
Assalamualaikum, sir.
Walaikum salam. Thank you.
Sir, it will be easy to upscale the biodecomposer.
I couldn't.
It will be easy for us to manage the upscaling of biodecomposer.
There are challenges. I said there are challenges because under controlled conditions, microorganisms, they are really pampered and they get each and everything what they need, in fact. But in the actual environment, it is something really difficult, and that's why we are trying, for example, solid state fermentation and liquid fermentation. So we are working on different And then definitely certain stabilizers as well, so that their life or their ultimately they are not affected by the environmental conditions. So that is a challenge, to be frank. And we are trying to see how we can address this issue.
Other question? Thank you.
Thank you.
Okay.
This one. पहले क्लोज कर लें इन यूज है इसको क्लोज करो Thank you.
Merci beaucoup, professeur Achad. Okay, now I would like to invite Professor Dr. Mudassir Asrar, Advisor Science Policy YC Comstech, for closing remarks. Yeah, Professor.
Bismillahirrahmanirrahim. Honorable speakers, Dr. Diallo, Mr. Akim, and dear participants. As we conclude today's webinar, I would like to extend my sincere thanks to our wonderful speakers, our distinguished speakers, for their wonderful and valuable presentations and for sharing their knowledge with us and the new technologies they are working on. This discussion today have clearly demonstrated that the waste is not only a byproduct of our activities, but is a useful resource when managed through innovation and collaboration. The sustainability is achieved when scientific creativity aligns with practical solutions and strong institutional commitments. Let's take forward the knowledge gained here today to inspire further research and implement innovative solutions that protect our planet for further generations. Together, we can turn today's ideas into tangible projects. Thank you once again for your participation and look forward to our future collaborations. Thank you very much.
Thank you, Professor Mudassir. Before go to the group photo, I would like to invite 5 persons for certificate. So first person, dear Professor Mudassir, please come for the first person. I would like to invite Atika Murtada. Sumera Hassan. Yes.
All out different certificates. You can. Okay. So next is Shumaila Hissam. Sorry? What? Miss Humaira. Dr. Muhammad Ayaz. Mr. Uzair Khan.
Hussein Khan.
Sorry?
Okay, please join us for the group photo. Yes. No.
Certificate for all?
Yes, they will give them.
We can give them no issue. Okay. We can, because otherwise. No, we can give them no.
Nimra Aman. Lareb Nadim.
Very easy.
Lareb Nadim. Sarah Adil. Alkama Nawaz. Alkama. Huma Murtaza. Mumtaz. Rishma Khatak. Miss Aisha. Mr. Zimal Said. Miss Javeria Majid. Miss Javeria Hamid. So please join us for the group photo. Just after group photo, there is refreshment over there. Please come.
Group photo will be here.
Yes.
आगे कुछ बैठ जो देख लो अरेंजमेंट बनाओ शाबाश आगे
This is Mustafa. Thank you. We have a refreshment.